Hello everyone. In this video we'll look at past year JEE Mains and AIEEE questions from the topic units and measurement. This is a part 1 of the video, and in the subsequent videos we'll be able to cover the remaining questions. So we'll start with a question in 2002. Incidentally, you may be knowing that the AIEEE examination has started from 2002 onwards. We need to identify the pair whose dimensions are equal. So here four pairs of physical quantities are given. Option A, we have torque and work. Option B, we have stress and energy. Option C, we have force and stress. Option D, we have force and work. So we need to identify which of these pairs will have the same dimensions. Now when we are answering any questions on the dimensional formula, we need to be knowing the dimensions of the physical quantities involved. Now there are two ways of doing it. One is we remember the dimensional formula of the physical quantities, which might be a little bit more tasking. Other approach is to have an quick approach where we'll be able to arrive at the dimensional formula of the physical quantity by using the most suitable formula. So what it is, we'll be able to see through in this particular solution. So first we'll start analyzing from option A. So we have torque and work. Now torque is the turning effect of force, which is given by force multiplied by the perpendicular distance from the axis to the point of application of force, which means torque dimensional formula will be force dimensional formula mlt power minus 2 into L, which will be m L square t to the power of minus 2. Work is given by the dot product between force and displacement. Again, what we'll have is mlt power minus 2 into L. Displacement is, after all, shortest distance between the initial point and the final point. So dimensional formula will be again ml square t power minus 2. So what we are able to see is that the torque and work will have the same dimensional formula, and of course here I would like to mention that the units of torque and work are represented differently. So the SI unit of work will represent it as joule, and the SI unit of torque we will represent it as Newton into meter. The reason being these two physical quantities are different, they do not represent the same quantity. So though the dimensions are same, we represent the units to be different because these two are two different physical quantities. Now we have various such examples of quantities which may have the dimensional formula to be same, and we can now mark the option as A, but for the academic interest we can look at the other options as well. So if you look at stress is if you look at the longitudinal stress, I mean a force is applied to either elongate the object or to compress the object. Let us say the area of cross section is A, then stress is given by the force per unit area. So which means it will be m L t power minus 2 force dimension divided by L square. So m L to the power of minus 1 t to the power of minus 2. That will be the dimensions of stress. And we can see energy and work will have the same dimensions, which means the dimensions of energy will be m L square t power minus 2, which means these two will not have the same dimension. And we can look at the force and stress. As we have just seen, force dimension is m L t power minus 2 and stress dimension is m L power minus 1 t power minus 2. So these two also will not have the same dimension. And force and work, of course, force is m L t power minus 2 and work is ml square t power minus 2. So these two also will not have the same dimension. So the correct option for this is answer A, which is torque and work. Now we'll move on to the next question. The dimensions of 1 by mu naught into epsilon naught. So mu naught is the permeability of vacuum or free space, and epsilon naught is the permittivity of vacuum or free space. Here sometimes, like they have done, they would not really give the description of these quantities. So we are supposed to remember the description of these common notations that we follow in physics. Now we need to find the dimensions of this. We may recall that in electromagnetic waves topic, we have the expression for speed of light in vacuum, which is given by 1 by root of mu naught into epsilon naught, which would mean that if we square on both sides, c square will be 1 by mu naught epsilon naught. Now we are looking for the dimensional formula for 1 by mu naught into epsilon naught, which will be the dimensional formula of c square, and c is the speed of light in vacuum or free space. So the dimensional formula will be speed or velocity dimensional formula is L t power minus 1 whole square. It will be L square t to the power of minus 2. So this will be the dimensional formula for 1 by mu naught into epsilon naught. So the correct option for this is option C. Now we'll go to the question that has come in 2003. The physical quantities not having the same dimension. Now here we have 4 sets of physical quantities. Option A, we have torque and work. Option B, we have momentum and Planck's constant. Option C, we have stress and Young's modulus. Option D, we have speed and mu naught into epsilon naught whole power minus half, which would mean this is nothing but 1 by root mu naught into epsilon naught. So we look at the solution for this. So first we have torque and work. Now torque is the turning effect of force, which is given by the force multiplied by perpendicular distance between the point of application of force and the axis. So it will have dimensions of m L t power minus 2, which is the force dimension, into again distance. So the overall dimension of torque will be m L square t power minus 2. And work, of course, is the dot product between force and displacement. So work also will have the dimension of force multiplied by the displacement, which is again the dimensions of displacement is L. So overall dimensional formula will be m L square t power minus 2. So we see that torque and work, they both have the same dimension. Now when you look at option B, which is momentum and Planck's constant. So momentum, so here we are referring to the momentum as a linear momentum. So linear momentum will be mass times velocity, which will be equal to m L t to the power of minus 1. And Planck's constant h. So to know the dimensional formula for Planck's constant, we may use the Planck's quantum theory. So as per the Planck's quantum theory, the energy of the radiation E will be equal to h times nu. Nu is the frequency of the radiation. So energy is m L square t power minus 2, which will be equal to h. So we're trying to find the dimensional formula for h into the dimensional formula for frequency. Frequency is 1 by time period. So the dimensions of frequency will be t to the power of minus 1. So what we'll have overall, so when we bring the t to the power of minus 1 to the LHS, m L square t power minus 2 divided by t power minus 1. So the final dimensional formula for the Planck's constant will be m L square t to the power of minus 1. So what we see here is the dimensions of momentum and Planck's constant. These two are different. So the right answer for this would be option B. Now for the academic interest, we can go and look at option C and option D as well. Option C is stress and Young's modulus. Now if you look at the Hooke's law formula in case of the longitudinal stress or longitudinal strain, what we have is stress is equal to Young's modulus into strain. Now strain is a dimensionless quantity, because when we talk about the longitudinal strain, it is the change in length by the original length. It will be dimensionless quantity. So the LHS dimension, which is the stress, will be equal to the dimensions of the RHS physical quantity, which is Young's modulus. So stress and Young's modulus, they both have the same dimensions. And similarly, if you look at option D, we have speed and the 1 by root mu naught into epsilon naught. In electromagnetic waves, we have a relation between the mu naught epsilon naught and the speed of light in vacuum. That is, speed of light in vacuum will be equal to 1 by root mu naught times epsilon naught. Now it would mean that the dimensions of 1 by root mu naught into epsilon naught will be same as the dimensions of the speed of light, which is of course the speed. So the option D, physical quantity speed, and 1 by root mu naught into epsilon naught, these two also will have the same dimensions. So option B, momentum and Planck's constant, they have different dimensions. And maybe you might want to check at a later point of time that the angular momentum and Planck's constant would have the same dimensions. So we'll move on to the next question. This is a question that has come in 2004, where we have to find out which of the following represents correct dimensions of coefficient of viscosity. Now not very often we'll get such straight questions where we'll have to find out the dimensions of the physical quantities that we use. So as I've been mentioning before, when we need to find the dimensional formula of a physical quantity, we need to look at most appropriate formula by which we can find the dimensional terms. Now when you look at the coefficient of viscosity, we have 2-3 formulas in our syllabus where the coefficient of viscosity will be appearing, but among them probably the Stokes law will be more appropriate to find the dimensional formula. So as per the Stokes law, the drag force acting on an spherical object, so if you have a spherical object of say radius r, it is moving with a speed v through a fluid whose coefficient of viscosity is eta, then the drag force, which is the force that will oppose the motion of the spherical object, which will be of course acting in a direction opposite to the velocity. Drag force acting on the spherical object will be given by 6 pi eta r into v. Now in this particular equation we have force, we have eta, we have r, radius of the sphere, and we have v, which is the speed or the velocity. Pi of course is a numerical constant that will be dimensionless. So LHS, if you look at it, we have force, which is ml t to the power of minus 2 should be equal to RHS. 6 and pi both are numerical constants, will not have any dimension. Eta, for which we are trying to find the dimension, into r is the radius, dimension will be length, and speed or velocity will be lt power minus 1. So we are trying to find the dimensions of eta, so we'll bring the other two to the LHS. So what we'll be finally having is mlt power minus 2 divided by l square t power minus 1 will be equal to the dimensions of the coefficient of viscosity. So upon cancellation, what we'll be having is m l power minus 1 t power minus 1. So this will be the dimensional formula for coefficient of viscosity. So the correct option is option C. So we'll look at the question that is coming 2005. Out of the following pairs, which one does not have identical dimensions? So we have pairs of quantities again given over here. In option A, we have moment of inertia and moment of force. Moment of inertia is the measure of inertia in the rotational motion of a rigid body. Then we have work and torque. Then we have angular momentum and Planck's constant. Then we have impulse and momentum. So we need to find out which of the following does not have rather same dimensions. So we look at the solution. First one is moment of inertia. So if you have an object of mass m which is rotating about an axis where the distance of the object from the axis is r, so here we are looking at the object to be a point mass. The moment of inertia of this object I will be given by m times r square, which means the dimensional formula for the moment of inertia will be m l square. That will be the dimension of moment of inertia. And moment of force. Moment of force is defined more along the lines of torque. So moment of force will be given by the product of force with the distance, which means the dimensions of moment of force will be mlt power minus 2, which is the dimensions of force, multiplied by distance, which is again length. So the dimensional formula will be ml square t power minus 2. So what we are seeing is clearly that the moment of inertia and the moment of force will not have the same dimension. So straight away we can mark option A to be the right option and move on. But for the academic interest, we look at the other options as well. So if we look at work and torque, work is the dot product between force and displacement, which means it will be having the dimensions of mlt power minus 2 into L, which is ml square t power minus 2. And torque is force multiplied by the distance, perpendicular distance from the point where you apply the force to the axis. So this also will have mlt power minus 2 force dimensions into distance L. So the overall dimension will be ml square t power minus 2. So torque and work, they both will have the same dimensions. Angular momentum and Planck's constant. Again, if you see angular momentum for a particle of mass m, which is moving with a speed v in a circular path of radius r, the angular momentum will be given by mvr. So the dimensional formula will be mlt power minus 1 into L, which is ml square t to the power of minus 1. And Planck's constant, we can find out the dimensional formula by using the Planck's quantum theory, where we have energy of the radiation will be equal to h times nu. Nu is the frequency of the radiation. So this will give us energy dimensional formula is ml square t power minus 2 is equal to h into the dimensions of frequency will be t power minus 1. So overall we can see that the dimensions of h, Planck's constant, will be equal to ml square t power minus 1. So which means that the angular momentum and Planck's constant, they both have the same dimension. And coming to the option D, which is impulse and momentum. So momentum is here we are looking at the linear momentum, which is mass times velocity, mlt power minus 1. And impulse is it's a measure of impact of force, which is given by the force into the time for which the force is acting, which means if you have force dimension is mlt power minus 2 into t, that will be mlt power minus 1. So what we see is impulse and momentum, they have the same dimension. So the set of quantities that do not have the same dimensions are moment of inertia and moment of force. This is a question that has come in 2006. Which of the following units denote the dimensions of ml square divided by q square, where q denotes the electric charge? Now we have the options given as Weber. Weber is the SI unit of magnetic flux, and Weber per meter square, which is an SI unit for the magnetic field. Henry is the SI unit of inductance, self-inductance or mutual inductance, and then we have Henry per meter square. So we need to find out which of them will have the dimensions of ml square divided by q square, where q represents electric charge. Now electric charge is not a fundamental physical quantity and it is related to the electric current. Electric current is a fundamental physical quantity. So just to look at what will be the dimensions of ml square divided by q square. So what we have is ml square. So charge is current into time, so we'll have at whole square. So the dimensional formula for this ml square divided by q square will be ml square t to the power of minus 2 a to the power of minus 2. So this is the dimensions of ml square by q square. Now we can look at all the four options and check which of them will be dimensionally matching with the dimensional formula of ml square t power minus 2 a power minus 2. So if you look at the quantities that we have, the magnetic flux, Weber, dimensional formula for the magnetic flux will be ml square t power minus 2 a power minus 1. Now we can get the dimensional formula for magnetic flux by using the idea of electromagnetic induction, where we have the induced EMF will be equal to rate of change of magnetic flux. So the induced EMF will be equal to negative of delta phi by delta t. So we have this equation from where we will be able to find out the dimensions of the magnetic flux. And Weber per meter square is the dimensional formula for magnetic field. So we can find the dimensional formula for magnetic field by using the equation for force acting on a charged particle moving in a magnetic field. So we have a force which is given by BQV sin theta. So we can use this equation to find the dimensional formula for magnetic field, which is of course the dimensional formula for Weber per meter square. And Henry, if you look at the energy stored in an inductor when it is getting established in terms of the current, energy stored will be equal to half L I square, which would mean that the energy stored inside the inductor will be equal to half into L, which is the self-inductance, into I square. I represents the current. So using this equation we can find the dimensions of Henry, and once we know the Henry, we can find the dimensions of Henry per meter square. So when we look at the dimensions over here, what we are able to clearly see is Henry has the same dimensions as ml square divided by q square. So sometimes we may have to relate some of the physical quantities and try and find the answers, but in all these questions what we are seeing as an underlying principle is we must have one adequate or rather most appropriate formula which we can use to find the dimensions of the physical quantity. It may not be really possible to remember the dimensions of Weber per meter square, Henry or Henry per meter square, and that might even complicate the things if we try to remember so many dimensional formulas. So rather what we'll need to be doing is we'll have to remember what is the appropriate formula to derive these dimensional formulas quickly. So the correct option for this is option C, which is Henry. Now we look at a question that has come in 2008. So the dimensions of magnetic field in M, L, P and Coulomb. So here we are trying to express the dimensions of magnetic field not in terms of the dimensions of the fundamental physical quantities, but we are trying to also include Coulomb, which is not a fundamental physical quantity. Now when we look at magnetic field as such, so if we have a particle with a charge q moving with a velocity v, may be inclined at some angle with the magnetic field, then the force acting on this moving charge will be given by BQV sin theta. So where theta is the angle between the orientation of the velocity and the magnetic field. So here on the LHS what we have is force whose dimensions are ml t power minus 2 is equal to the dimensions of B. Of course here we'll have to get the dimensions of B in terms of mlt and charge dimension. So here we can take the charge to be having the dimension C. Normally we'll be expressing it in terms of current into time, but here as they are asking in the question, we will be continuing with C to be the dimensional symbol for charge, into V is the speed which will have dimension L t power minus 1. Sin theta trigonometric function is a dimensionless quantity. So we can see over here that L will get cancelled on the LHS and RHS. So we are looking for the dimensional formula for the magnetic field B. So we'll bring the other terms to the LHS. So in LHS what we have remaining is m t power minus 2 in the numerator divided by C into t power minus 1, that will come to the denominator. So will be equal to the dimensional formula for B. So overall what we have as dimensional formula for B in terms of m, L, T and Coulomb will be m t to the power of minus 1 c to the power of minus 1. So the correct option is option D. Now these are the questions from the past years in part 1 of this video. In the next video we'll look at some more questions from the past year AIEEE or JEE Mains from this topic, units and dimensions.